is an alpha particle. The daughter nuclei form. The daughter nuclei form. The daughter nuclei form. The daughter nuclei form is two places. The daughter nuclei form is two places to the left. The daughter nuclei form is two places. The daughter nuclei form is two places. To the left. Is two places to the left. It is two places. The daughter nuclei form is two places to the left of the parent nuclei. Is two places to the left of the parent nuclei. Is two places to the left of the parent nuclei in the periodic table. Is two places to the left of the parent nuclei in the periodic table. Is two places to the left of the parent nuclei in the periodic table. So now, go to II. Then II, so let's see the second statement. II, if beta particle is emitted, if beta particle is emitted, if beta particle is emitted, then the daughter nuclei is one place to the right. Is one place to the right of the parent nuclei. Is one place to the right of the parent nuclei. The daughter nuclei is one place to the right of the parent nuclei. Is one place to the right of the parent nuclei in the periodic table. Then III, if gamma radiation is emitted, then there is no change. If gamma radiation is emitted, then there is no change in the nuclei. Except that energy is released. So we can have you got it right?
International.
There's no change in nuclei except that energy is released. So look at this now. Now what this is saying is that very simple. Okay? Very, very simple. Now you have when a nuclei, okay? If a nuclei is at X, and then this is M, and then this is N, okay? Then if an alpha particle is produced, if an alpha particle is released, because an alpha particle has mass of 4 and then atomic unit of 2, okay? Because an alpha particle has mass of 4 and then an atomic unit of 2, what will happen is that this is the parent nuclei, remember? Okay, this is the parent nuclei, okay? The unstable nuclei. This is the unstable parent nuclei. So what will happen to the atomic units is that it is going to reduce by 2 now. Is it not true? It's going to reduce by 2. Why? Because this is producing an alpha particle. So the mass is going to reduce by 4, and then the atomic unit by 2. That means that the daughter nuclei that would be produced, if for example Y is the daughter nuclei that will be produced, then this shall be M minus 4. Is it not true? M minus 4. As simple as that. Okay? The mass is going to reduce by 4 units. And then what will happen to this one? This is going to reduce by what? By 2. Is it not true? As simple as that. So now Fajan and Sodi observed this. And then what did they observe? They observed that anytime an element, anytime a radioisotope releases an alpha particle, then what will happen is that the mass will usually reduce by 4. and then this other one by 2. And how did they want to now relate this to the periodic table? This is just relating radioactivity to the periodic table. If your atomic unit reduces by 2, what does it mean? It simply means that if you were element number 82, what will your total nuclei now become? Element number 80. And element number 80, is it not 2 places to the left of the parent nuclei that produced it? Is it not? As simple as that. So, this is what Fajan and Soddy developed into the group displacement theory. So this is the daughter nuclei here. Okay? So that if you release an alpha particle, then the daughter nuclei you are producing, of course, will be 2 places to the left of you in the periodic table. As simple as that. Then, however, if we produce a beta particle, okay, if however we produce a beta particle, then it shall be that if we have produced beta particle, so this shall be I, okay, according to how we tag them, this shall be I. Then if however the nuclei produces M now and then N, and then the nuclei produces a beta particle, okay, which are electrons, beta particle this, okay, then it shall be that this Y that is produced, okay, or in this case, you can just call it anything. C that is produced, okay, shall have the same mass. It shall have the same mass, and then but it shall be n plus 1. Do you observe? N plus 1. And why is it n plus 1? Do you observe that n plus 1 minus 1 will give you n? Do you observe? So at the end of the day, the daughter nuclei that we produced will be 1 place to the right. Is it not true? Why? Because the atomic mass is going, the atomic number is going to add by 1. Is it not true? So the element that we produced will be element number 83. If it were this now, it will be element number 83. Is it not true? As simple as that. Then, but however, if it is gamma, okay, then if it is gamma, then what is going to happen is that nothing is going to change. Okay, nothing is going to change. Okay, nothing is going to change except that energy will be released. Okay, so this is going to be plus energy. Okay, plus energy. Energy is going to go away. Okay, it's produced in that particular reaction. As simple as that. Okay, as simple as ABC, right? So let us see some nuclear reactions now. So let's see nuclear reactions. So let's exemplify nuclear reactions now.
In 2035, you come back and look at this video. $2035 now. You just enter my YouTube one day. Eh? Enter my YouTube one day and see yourself. Yes. Idoko and her friend. There's that one that doesn't like camera. La madame, que meginis? Himerura rueba. Did you enjoy yourself? My man. Okay, where you go? How are you now? Okay. Bye, can you? The Kene can make any. Oh, my students now. Mama. Okay, you're pressing your phone. From next year, you people will be in Park Lane Auditorium. Hmm? Yes. 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 Yes, now you be in college auditorium. Which department? Okay, so go a farm so hey so yeah, this place is for you people.
So let's look at this now. So let's look at this. So natural radioactive decays. Natural radioactive decays. Now, so let's see. The first one is 222 radon. Radon 222 decaying, undergoing alpha decay. Okay, undergoing decay, and then producing radium is producing radon 86, and then X. Now we have polonium 208 producing lead 204. Producing lead 204. And then Y. And then of course, Lawrencium. So we have others, which time may not even permit us to see. Iodine 131. Iodine 131. Producing xenon 54. Producing xenon 54. And then others. Okay, others that time will not permit us to look at. Others, okay? So when you look at more, when you see more, then of course you should be able to identify them. Okay? You should be able to identify them. So just identify them, try to identify them, then once you cannot do, you bring them back to class. Okay? So now let's see this now. So look at this. This is a very simple reaction. Okay, a very simple reaction. But now look at, you observe that I tagged this natural radioactive decay. Okay, this natural radioactive decay. Now look at this. Let me at this point remind you that certain stable nuclei, okay, can, for certain reasons, we can induce a particular nuclei to become unstable. I hope you know. Okay? For reasons that can be scientific. For scientific reasons. Okay? So that we can do some study. You know, human beings like to always go and do their own. Is it not true? After the one God did, human beings like to go and do their own. So now, we can also make a nuclei to begin to emit radiation. Okay? For scientific reasons, we can make a nuclide to, or change to nuclei of another atom. Okay? The nuclei of one atom to change to nuclei of another atom. Now that one now is artificial radioactivity. But that is why I decided to tag this natural. So it is natural when there is nothing reacting with the nuclei. I will show you now, in another reaction, I will show you now when it is artificial. So when it's artificial, you are going to observe that something else is reacting with the nuclei. Reacting with the nuclei here. Then for it now to give products. We're going to see that now, briefly. So let us identify these particles now. Let us identify these particles. So what shall this particle be? What shall this particle be? An alpha particle. I don't need to stress my line. Okay, you can already identify that what happened to the radium, okay, that changed it to radon, is simply that it reduced by 4. Is it not true? And then also by 2. So definitely, whatever should be X should be an alpha particle. It should be an alpha particle. Okay? So this man produced an alpha particle, and then you have a radon. Then polonium. Polonium is 208, and then 84. So now this gave the 204, and then 82. So what should it be now? Alpha. Alpha particle. Very good. So it should be alpha. Okay? It should be, definitely should be alpha. Then again, we have iodine. Okay, iodine 131 give xenon 131. Okay? Now this is 53 and then this is 54. So what do you think this is? Beta. Very good. That should be a beta particle. Okay? That should be a beta particle. So we have a beta particle there. Now, there are reactions where you can have more than one beta particle in one step of reaction. Okay? You can have more than one. You can have a number of beta particles. Okay? A number of beta particles in one line of equation like this. It's just left for you to be very thoughtful enough. Okay? Then for you to observe when and how the reaction occurs. Okay? Now, let's now see. Let's now see some other reactions that we can tag to the artificial. Okay? Let's see some other reactions that we can tag to the artificial. Let me save my time by just speaking the ones here. For example, we can have, do you observe nitrogen? Okay, we can have nitrogen 14. Okay, so let's call this one artificial. Okay, so artificial. Okay, so we have nitrogen 7. So if nitrogen 7 reacts with helium, okay, so we shall have oxygen 8.
What's doing that one?
Oxygen 17. And then a proton. Oxygen 17 and then a proton.
It's hunger.
Then
Did it before coming?
Uranium 238. Uranium 238.
Be strong.
Okay. Then is bombarded with neutrons, fast-moving neutrons.
No, it's 2035.
It is going to give uranium 238, however, and then gamma particle is produced. Okay, or rather, gamma radiation is given off. And then the same thing also happens. Okay, and then other examples. Let me just say other examples. Okay, lithium 6. The same thing with lithium 6. Lithium is what? 3. Okay. So lithium 6 and then a neutron. Lithium 6 and then a neutron will give us hydrogen. Okay? Will give us hydrogen. This isotope of hydrogen and then alpha particle is produced. Okay? Check it. Is it? Yes, it's correct. Okay? Then that is produced. So look at what is happening here. What is happening here is that, remember, you can artificially bombard a nuclei, if you bombard a nuclei, okay, using fast-moving particles. Fast-moving particles like neutrons, okay? Now, did you do, when you studied physics, did you study nuclear reactors? Did you learn what happens inside nuclear reactors? Like in my country, we use nuclear power. Okay? I don't know about your own country. In my country, we use nuclear power.
And what's the name of your country?
The name of my country? Yes, it's not necessary. I don't want people to come and kidnap me. So in my country, we use nuclear power. I heard that your own country uses hydroelectricity. That is not even stable. that is not even stable. That sometimes you just see it for 4 hours in one day. Okay?
One day.
Sorry, that's epileptic.
1 day.
4 hours is too much. Okay? So you can see. So what is happening here is that you are targeting a nuclei. A nuclei can be targeted, and then you use fast-moving particles and then hit the nuclei. When you hit the nuclei is going to react. When the nuclei reacts now, the product of that reaction will make you to form another nuclei. Okay? Will give you another nuclei. You see, human beings can just be mysterious. So now that means nitrogen. You are going to observe, this is nitrogen 14. Do you observe from just the little thing I taught you? Do you observe that nitrogen could be stable here? This is a stable particle.
Yes.
Okay, 7 neutrons and 7 protons. This is a very probable stable nuclei, is it not true? Then if you now shoot it with a fast-moving alpha particle, then what is going to happen is that it is going to produce a nuclei of oxygen. Okay, oxygen 17. It's going to produce oxygen 17. And then this is a proton. Do you see that now? Then look at this other reaction. Uranium-238, okay, uranium-92, is bombarded using fast-moving neutrons. This is a neutron, okay, using fast-moving neutrons. Okay, this is artificial. So if you bombard this nuclei, then what is going to happen is that it will still produce uranium-238. Do you remember when we did gamma rays? I told you in gamma, the nuclei remains the same, except that what? Energy is released. So this man is produced. And if you want to complete this equation, you can put also energy. Okay? And have you heard about the use of uranium? Have you heard about uranium? You've not heard about uranium. You've heard about uranium, right? And how countries use uranium to produce electricity, right? In your country. Okay, so now the last one is lithium. Okay, lithium, you can see lithium-6. So lithium-6 bombarded with a neutron. Okay, always look at the mass. You are going to observe that the mass is conserved. You see, 3 and 4 is 6 and 1. Okay, 238 and 1 is 238. Okay, thank God I saw that. So this is uranium-239. Okay, uranium-239. And then gamma is produced. So then here the same thing, 18 and then 18, very good. And then the lower ones are also conserved. So this is hydrogen. Okay, this is hydrogen. This hydrogen is produced. Okay, hydrogen-3 is produced. That is tritium, right? And then another alpha particle. Okay, so as simple as that. As simple as that. Now, let us now talk about radioactive decay. Which one do you not understand? The last one. Okay, the last one, if you bombard lithium, okay, using a neutron, using fast-moving neutrons, then what you're going to produce is hydrogen. Is it hydrogen-3 that is giving you the problem? Hydrogen-3. Okay, became 239. Okay, the reason is because we needed to conserve the mass here. Okay, 238 plus 1. If not, then it will not be balanced. You get? If not, it will not be balanced. If not, here will be 239, and then here will be 238. So we need
This
the mass to
guy
be
always
balanced.
asking questions.
Remember, gamma is 0 and 0.
Question
now.
asking. Yes.
Okay, gamma is 0 and 0. So if not, then we'll be losing mass of 1. Okay? So as simple as that. So let's go to now, let's see radioactive decay. So let's see radioactive decay. Radioactive decay.
Yes, sir. Yes, well. And once I post it, I delete it.
Now, you have to listen carefully here. You have to listen carefully here. Now, radioactive decay, we want to see what happens within a nuclide, okay, if it is undergoing radioactive decay. Now, I will explain it in a very simple way. Let this be a graph. Let this be a graph. And then this particular axis, let this axis, okay, be the number of decaying nuclide. Number of decaying nuclide. Number of decaying nuclide is here. Number of decaying nuclide is this axis. Okay? So this axis, the number of decaying nuclide. Okay? This is 0. So the number of decaying nuclide, let us call it N. Number of decaying nuclide, this axis. And then this other axis is time. This other axis is time. This other axis is time. So time T. Okay? Whereas this is N, this other axis is what? Is time. Now, the graph of radioactive decay is usually like this. It has this nature. The graph of radioactive decay is usually like this. It has this nature. Okay? It's usually like this. Now, let me just show you something. Let me show you something. Now, what this is simply illustrating is very simple. What this is illustrating is very simple. If, for example, you have chalk. Let me use chalk. To illustrate it, to give you an analogy. If, for example, you have chalk, and this is the mass of the chalk. This place is the mass of the chalk, and then this is the time. This is the time taken. Do you observe that if, for example, I keep 100 grams of chalk, if I bring 100 grams of chalk now, follow me now. If I bring 100 grams of chalk and keep it under the sun and the rain, I want to know the effect of sun and rain on a piece of chalk. So I bring a piece of chalk now and then keep it under the rain and the sun. Then I always check it after every one week. After every 1 week, I come and check. I check the chalk and then weigh it. Now, I started with 100 grams of the chalk at zero time, when time has not elapsed. Okay? At zero time, when time has not elapsed, I have 100 grams of the chalk. Now, after about 1 week, I came back. This is 1 week. After 1 week, I came back. Will that chalk still remain 100 grams? No. As rain falls on it, it beats up some particles. Is it not true? So definitely, as time elapses, then the chalk will reduce in mass. Is it not true? So maybe by 1 week when I came back, the chalk could be remaining 80 grams. So the chalk is remaining 80 grams after 1 week. Then after 2 weeks now, by the time I'm coming back within the second week, it may have reduced to 50 grams. Okay? So after about 2 weeks, it reduced to 50 grams. Okay? Then after about 3 weeks, what happens? It reduces to maybe 25 grams after about 3 weeks. Then after about 4 weeks, it reduces to 10 grams. And then on and on and on. At the end of the day, if you join this, what will it look like? It will look like this. Is it not true? Yes. To tell you that as time elapses, then the mass of the particular chalk is reducing. Now, that is also happens with the nuclei. When a nuclei is undergoing radioactive decay, remember, it is losing mass. Is it not true? So, as it is losing mass as time elapses, okay, the number of decaying nuclei, this particular nuclei will keep decaying and reducing in mass, And the point, so this point now, where we started, the point, if you interpolate this now, if you interpolate that particular line, if you interpolate that graph, you get to this point. Let us call this point N0. N0 is at the point when nothing has decayed, the original number of nuclides. So N0 is the original number of nuclides. Okay? The original number of nuclides. At time t equal to 0. When nothing has decayed. Okay? So at time t equal to 0, we have N0. Now, we also have another one. There is this point now, we call the N0 over 2. Okay? N0 over 2 is when what you started with has come only half. So if I started with 50 grams, then at N0 over 2, what will it remain? 25. If, for example, you are meant to live 100 years, assume you are meant to live 100 years, at 50 years, what have you done? You have lived half of your life, right? Yes. At 50 years is your half-life. 50 years is what? What do I call it? Your half-life. That means when what?
50 years is your half-life. I see your whole half.
Okay, people are trying it to live. But wait, you don't want to live up to 100. But it's not by eating ice cream and Indomie. Okay? People who have lived long know that for you to live long, you need to eat good, right? So anything
You need to eat up.
Follow me now, follow me. I want to end. Any zero over 2 is what we call half-life. Okay, so this point is the point where this particular nuclei have decayed to half. So here, let us label it T half. We always write it at T half. So T half is the half-life. Okay, the half-life. We call it half-life. Okay, half-life of the radioactive nuclei. So that means when any zero have decayed to half, so you have half of any zero. Okay, so if we started with 100 grams, then we have 50 grams. This point where this particular thing is 50 grams is called the half-life. So that simply means that from what we have here, the half-life of this chalk is what? Is 2 weeks. Is it not true? The half-life is 2 weeks because it took 2 weeks for it to reduce to half. Okay? So the half-life is the time taken for half of the radioactive material to decay. So that is the half-life. So T half is the half-life. Then, of course, N is the number of decaying nuclei. Okay? Or the remaining number of nuclei at any time T. Okay? So the remaining number of nuclei. Okay? The remaining number of nuclei at any time T. At any time T. Now, having established all of this, let's now go into the mathematics of it. Now, I shall say that the rate of decay of a nuclei is proportional. Okay? The rate of decay, we shall say mathematically, we shall say that the rate of decay so D N over N, okay? N over N is proportional to time. Or rather, let me specify it this way. Wait. Don't be running too fast.
What happened to your head? Looks like you're covering your head. So after chemistry, we do small physics. I'll buy you, don't worry. After, yes, I will. After chemistry, we do small physics before we go on. But wait, so why is it that if we say we do small class, you'll be shouting? Are you not a student? You're supposed to be a soldier. Very strong. Mama, you started today, Shebi? When did you start? The last week. Hope you've paid small thing for tutorials. Okay, you're looking small. Okay, and welcome. Nikwayo, wounded lion. Yes, you tell me it's 4 o'clock. I'll tell you. Queen Agapa clean. Euro College Auditorium is here at 4 o'clock.
Is proportional to n. Okay? Minus the n over the t. Minus the n over the t is proportional to n. Okay? Okay, I should define it. Okay, I was saying the rate, okay? The rate of decay. The rate of decay of a radioactive nuclide. The rate of decay of a radioactive nuclide is proportional. Okay? The rate of decay of a radioactive nuclide with time. Please put with time there. With respect to time. With time. Just put with time. The rate of decay of a radioactive isotope, okay, or element, anyone who wrote, of a reactive nuclide, anyone who wrote, is proportional with time. Is proportional to the number. Is proportional to the number of remaining nuclide. Is proportional to the number of remaining nuclide. Is proportional to the number of remaining nuclide. Remaining, if is proportional to the number of remaining nuclide. Remaining nuclide at any time. So look at this now. See the best way to explain this. The rate at which a nuclide is reducing, okay, is proportional to, with time, with respect to time, is proportional to what is remaining. Is proportional to what? To what is remaining. Now look at this. You observe that some of you, when immediately you come back from school, by the time you travel home now, you go for Christmas, you are going to observe that your uncles will come around and give you money. Is it not true? So by the time you are coming back in January, we observe that you people are loaded. Okay?
Then we increase tutorial fee. Then we increase tutorial fee.
Then we are going to increase tutorial fee by then. So we are going to observe that now, when you come back in the first week, okay, you'll be eating in the evening like this. You say, hi, Oga Frayo. You know Oga Frayo?
No,
yes. You have not known.
certificate.
This one knows.
No, brought that certificate.
Oga
You're the one that paid me
Frayo
for
is
birth
the man
certificate.
in this man that sells pork.
Why do you want to pay me for birth certificate?
Pork. Pig meat.
Okay.
Pork. Now, some students will always go to Oga Frayo in the evening like this and go and chook pork of 2,000. Okay? Why? Because your pocket is large. I saw a picture. Somebody drew 4 pictures.
Savio himself.
He now wrote, first week after salary, chicken and indomie and everything.
You don't come for class yesterday.
After salary,
You don't come the days you like.
1 week after salary,
Okay.
1 week after salary, So,
Eden, how are you now?
as which we are considering
Ukwachukwu,
is the
computer scientist,
of all what is remaining.
my students.
Does not make sense. When you get back early,
But 2035, I'm going to give you a good achieve. If you're on YouTube, you need to
when you now come and say, hey, I'm hungry like this, you don't say, just like me.
food man. I will book you. For your food.
And you give your friend 2K, and they get something. But by the time your money now remains
They will pay.
5,000. Your friend will have to say, I'm very hungry. You say, or you now can manufacture English that does not exist. Even me, I am hungry. So, the rate at which you are consuming money is dependent upon what is remaining. It varies as what is remaining. Now let us do mathematics on this now. So we are going to do, we say that minus here, let us remove this proportionality sign. If you remember, in mathematics, if you remove proportionality sign, you will introduce what? Very good. So let's remove this out. So we say minus n over dt is equal to lambda n. Lambda is our constant. So we call lambda the constant of proportionality. So the constant of proportionality. So constant of proportionality. Okay? So you call this, our lambda is our constant. So this is our constant. Then let us now do simple mathematics. Okay? Let's rearrange this equation. So if we rearrange the equation, okay? If we rearrange the equation, we're going to have that dn, let n come down and let dt go up. Okay? So we're going to have that dn over n is equal to minus lambda dt. Am I correct? So the minus, I multiply both sides by minus 1. Okay? Minus times minus here is positive. Then minus times this other place will give us negative. Then the lambda is still there. Then I threw the t up and then bring n down. Okay? It's as if I cross multiplied, then my n came down and then my dt can go up. Okay? By cross multiplying, my dt can go up and then my n come down. So I have the n over n is equals minus lambda dt. Then what I shall do now is to integrate. Okay? So if I integrate both sides, okay? So if you integrate both sides, so let us see what we're going to have. So we integrate now, so we have the n over n, okay? If we integrate, is equal to, we're integrating lambda, that is dt. Okay, we're integrating dt. So if I integrate the n over n, then what it will give me is ln n. Ln n is equal to, then I have minus lambda. Okay, so minus lambda then t. Okay, if you integrate dt, you are going to have t. Okay, then plus constant, plus c. So if you are going to have ln n, now do you know what ln is? Ln is logarithm to base e. Most I have not taught you in logarithm. You have not learned ln in logarithm. Have you learned logarithm at all? Yes. So how come you did not come across ln? Where is your scientific calculator? You've not seen ln on your scientific calculator. Very close to logarithm. Close to logarithm. This girl has calculator. This girl has scientific calculator. Can you see it? Can you see it? ln. That is ln now. Yeah? That is ln.
Gary.
Ln. Okay? So ln is logarithm to base e. ln is the same thing as logarithm to base e. Okay? Logarithm to base e. And you know what e is? Okay? E is the 2.718 kiniko is a constant. I hope you know. It's a transcendental irrational number. Just like pi. Just like pi. You've not studied deeply these numbers. You've not studied them. Why should I? Somebody said, why should I? Is it my business? Okay? Somebody said, is it my business? Why should I like that. I like that. Why should I? You should though. Okay? So, now, if you do this, if you have this now, then what you shall do is, let us go back now. So let us go back a little bit. Okay? Let us go back a little bit. Eh? You don't understand? Okay. Now, where did we lose you? At this point? Yes. Okay, but do you know how we rearranged, right? No. You know how we rearranged. Okay, we have this now. Minus the n over the t is equal to lambda n. We have cross multiply. Cross multiply. If you cross multiply, what do you have? Minus the n is equal to, so cross multiply. So dt times everything here. So have dt lambda the n. Okay, or lambda n dt. Okay, lambda n dt. Then we divide both sides by n. Okay, we divide both sides by n. So if we divide both sides by n, if we divide both sides by n, okay, if we divide both sides by n, this is n, dividing both sides now. Then n can cancel out n here. Okay, then we cannot cancel this out. This is change in N. So you cannot cancel it out. How do you know? This is change in N. Okay? It's just like saying, do you know the origin of differentiation and integration? Now, it's not a problem. It's not a problem. Okay? It's not a problem. Have you ever plotted graph before in physics? Yes. Have you ever plotted graph in physics? Yes. Have you ever looked for slope? Have you ever looked for slope? What do you do when you want to get slope? You do change in y, right? Over change in x. This is the origin of differentiation. Change in y over change in x. If this is that the x, the y, the x you are talking about. That the y, the x you are talking about. You simply want to know at the rate at which this is changing, this function is changing in this axis compared to how it is changing on this axis. I think it's what the origin is. Anywhere at all there is change, then differentiation becomes valid. It becomes useful. Your age yesterday and your age now, I hope you know it's not the same. You are changing.
It is different.
So we often say that change is inevitable. It's not true. So in life, at any point in time, there is change. And so we cannot cancel
from
this
the word
out.
different, you get differentiation.
We cannot cancel this out. So what are we going to have now? Now, minus the n, right? Over n, right? Then is equal to lambda, right? D and then t. Is it not true? Then we multiply both sides by minus 1. If we times both sides by minus 1, what are we going to have? Minus times minus, plus, right? So the n over n is equals minus times what we have here. Minus, right? Minus the t. Are we not, haven't we gotten what we have here? So the n over n is equals minus lambda the t, right? So it's nothing very serious. Okay? Then we now integrate. If we integrate, anytime you integrate, let's not go too far. Anytime you integrate the whatever over, if you integrate the P, pressure, okay, over P, okay, then it is going to give you ln P. Okay? That is logarithm to base E. Logarithm to base E of P, of the quantity P. Does it make sense? What's the no again for? What's the no for? You are tired? It's a constant. Yes. So now let's move further. You don't need to understand this, so. Assuming you don't understand it, will you not eat this night? You eat, yeah? You don't eat.
Do you have your browser? Let me check
That's what you should be
something.
asking me.
Like,
Okay?
is your browser active? Let me check.
Thank you very much. Somebody said, what is C? This is constant of integration.
Sure,
The C
better.
then is constant of integration. This is constant of integration. Okay? Constant of integration. Anytime you do integration, okay, then we usually have a constant. So the C is the constant of integration. Okay? This is the constant of integration. So let us now do something. Let's do something now. We're almost finishing. So look at it now. If we now say at time, okay, let us put in at time, okay, at time t equal to 0. At time t equal to 0, what do you observe? N is equal to what? N 0. Is my statement correct? Yes. At time t equal to 0. Now look at this. What this simply means is that when time has not elapsed, what is remaining at that point in time? What is remaining? When time is equal to 0, what was remaining? Everything. Thank you. Everything. Okay, come and take. Everything is remaining. I like the way he said it. Okay? I like the way he said it. He used energy to say the thing. Okay? At time t equal to 0. This is what he said. I like you to always follow me when I'm teaching you.
Yeah, thank
always
you.
follow me. Okay?
Thank
Energy. How you know energy is good? Always follow me. So at time t equal to 0, n is equal to what?
Give us money.
Excess energy.
Well, no well.
That is excess energy. Now please look at this. Okay, please look at this. My HOD is waiting. So look at this now. At time t equal to 0, n is equal to n is 0. Put that into this equation. So let's put it into equation. So if we put into equation, what do you have? You shall have that ln n equal to minus lambda t plus c. That means where I see t, I put 0. So that means that ln n now, n will become n0. That is n0 is equal to minus lambda bracket 0. Is it not true? When time is 0, n is n0. So put it into this equation that you formed now. So ln n0 is equal to minus lambda 0 plus c. So 0 times this now will give you c. Is it not true? So that means that ln n0 is simply equal to c. Put this back into the main equation. This can be b. You can call this equation A. So put this back into the equation. Put into equation B. Put it back into equation C. That ln n0 is equal to C. If you put it back here, you have that ln n is equal to minus lambda t plus ln n0. Then take this to this other side. Ln n minus ln n0
Put
is
it.
equal to minus lambda t.
Shall we put into A?
Not B.
Put into A. Thank you.
Yes.
Put into A. Okay? So if you put it into A, that means C is equal to ln n0. So C is ln n0. Put it here now. Okay? So ln n is equal to minus lambda t plus ln n0. Then collect like terms. Okay? Collect terms. That means ln n0 should go over to this other place. So ln n0 is equal to minus lambda t. Now, if you have learned log reading, log A minus log B, what is it now? Is equal to what? Is it not log A over B? Very good. Very good. Master Parker taught you that. If you apply that here now, since I told you that ln is exactly the same thing as log, okay? So ln n minus n0 will give you what? Ln n over n0 is equals minus lambda t. Have you seen this equation before? Yes. Good night.
The prof himself. Oh yeah, let's do physics. Okay, now what's the time? What's the time? Don't worry. What's the time? Check. Okay. Oh yeah, somebody pray for us. Hope you learned something. So please, if you go home, you revise it. The good thing is that today I will still repost this video. I'll still post this video to the group. Then we'll find additionals. Then we'll post on the group. So you use it to study on that paid tutorial group. So please, if you've not joined the paid tutorial group, notice that